Good morning. So we have made our way through chapter 4. We have made our way through most of chapter 5. We're going to finish up chapter 5 today. And again, I hope you guys are taking all this in. This is kind of the core of the entire course. I'm going to say the Physics 4A course is best represented by the topics that we've been looking, the dynamics that we've been looking at in these chapters, taking forces and relating them to motion. Now, at the last class meeting, what we had done was we were looking at this example. We were swinging this ball in a vertical direction, in a vertical circle. So in a vertical plane, this was circular motion, and the mass of the ball, 150 grams, the length of the string, not the length of the string, so I should be clear on that too. So it's center, where the string is being held, to center. So the string's actually a little shorter. So they called it a 1.10 long chord. We are assuming when we say that, we mean center to center distances. So it's center to center for the vertical motion, and then what we did was we assumed we were spinning this just fast enough at the top that it maintained a nice circular path. And then we asked, if that's the case, what's going to happen to the tension at the bottom? So in order to just make it through and maintain that nice circular path, we said at the minimum speed, the tension will drop to 0 just momentarily right at the top. The tension will be 0. When we calculated that out, we calculated a speed of 3.28 meters per second. Now that came from saying the only remaining force, the force we're going to depend on at the top to maintain circular motion, is gravity by itself. So there's a gravitational force at the top. We can divide that through by m. That leaves us with g. And then plugging that into our acceleration formulas, saying the acceleration is equal to g, we got a velocity that was 3.28 meters per second. And then we said, they said, imagine at the bottom that the speed is going to be twice as large. Now, if the speed is twice as large, the acceleration will be 4 times as large. At the top, the acceleration was g. So now the acceleration at the bottom is going to be 4 times g. It's going faster. There's going to be a larger acceleration. That means we need a larger force. If I've got a lot more acceleration going on, if I have 4 times, let's use the numbers, if I've got 4 times the acceleration that I had at the top, I'm going to need 4 times as much force. Now that 4 times g is actually in this direction. So the tension at the bottom, it can't go to 0. The tension at the bottom is going to have to create that 4g, plus it has to offset gravity. When we set that up using the equations of motion, what we found was that the tension needs to offset gravity and provide an acceleration of 4g. That got written as 5 times mg. So the tension here then worked, and we put the numbers in. It's not a very heavy object. The tension that we would need at the bottom, 7.35 newtons. All right. So good problem, right? Good practice with force diagrams, with circular motion. That's what we need to be able to do now that we're into chapter 5. All right, here's another circular motion example with, is it the very same sphere, again, the same ball? Small ball of mass, it's just mass m this time. So they're going to have us do all the algebra. We could put some numbers in later if we want, but as you notice, when I'm doing these examples, it's all algebra, right up to the end. And that's because looking at the algebra formulas will tell you something about what's going on. So let's do this. Now, if I have this, it calls it a cone pendulum. So I've got this circular motion, and that circular motion is forming kind of a circumference at the base of a cone, and the string is kind of marking out the conal shape. So that string that's tied at that one point at the top, it's going to form a cone shape by the time it swings around. So what that says is this. It says that the tension I have is along the string. If I have a flexible object like a string, the tension has got to be along the string. If I have a sideways force on a string, the string is floppy. The string will go in whatever direction the force is in. So the only way you would have a string along this direction is to have the tension lined up right with it. Now, the tension then is in this direction, and what you can see on the force diagram is we are going to want to separate the tension into a radial component and this vertical component. Now the vertical component, they are bringing back in unit vectors, and that's fine. I don't know that we need them here so much, but it's not a bad idea to think in terms of unit vectors. Now, as the ball goes around in this horizontal plane, the force is going to continue to be towards the center. So that's why we're thinking more in terms of a radial direction than bringing in I or J. I guess J stays the same. So the vertical force stays the same all the way around, but the radial directed, the centripetal force, has to keep changing directions because it has to keep pointing towards the center of the circle. So they've given away some of the stuff here. So let's see what's happening. Where is the center of the circle? And at first you might think, oh, the center of the circle is here, but it's not, right? The center of the circular motion is here. This is the radius, and they've labeled that as r. So r is actually equal to L. L is the length of our string. And then we want to take the sine of theta to get the opposite side of that triangle. So r is going to be equal to L sine theta, just like they say, where theta is the angle between the vertical and where the string is that makes up this cone. Now, what direction is the acceleration in? And the acceleration is towards the center of the circle. So I've got a circle mapped out here. That is showing the circular motion. There is a center to that circle, and the direction of the acceleration is going to be centripetal towards the center of the circle. The force that is maintaining the circular motion will also be in a centripetal direction. So what we can do is we can take the tension force, we can divide it up into components, vertical and radial, and then we can assign a meaning to this. The vertical component is going to offset mg. So while this is operating, there's going to be a force of gravity, and the vertical component from this string needs to be balanced with the gravitational force. And that's what's going to be happening. If we get this so that it's forming these really nice circles, maintaining the same radius r, then at that time we will know that the vertical component here matches mg. Meanwhile, the radial component is going to be associated with circular motion. So the radial component gives us radial acceleration or centripetal acceleration. That's the circular motion. So let's pay attention to these components. Now what they want us to come up with, and I know I got to read the problem carefully, in what direction is the acceleration? What force is causing the acceleration? And we've covered that. So the acceleration is towards the center of the circle. It's going to be in that direction. And the force providing that acceleration is the tension times sine theta. So that's it. B says calculate the speed and the period of revolution. How much time does it take to go around once in terms of L, theta, G, and M? So let's do it, right? Let's get those formulas set up, take a look at the, solve, set up the algebra, solve for, what are we solving for? The speed and the period. Let's read carefully. So here's the diagram. So here is the ceiling or whatever, and we've attached the string, and here is this object. It's going around in circles. And if it's perfectly balanced, then we can take a diagram at any location, and that will work. So we'll pick the same location they did. So here is mg pointing downwards. Here is the tension force angled like this, and then here's our force diagram. So I've got T cosine theta equals mg. That's in the vertical direction. Now in the radial direction, or the centripetal, the acceleration is equal to the net force divided by m. So the acceleration will be a result of T sine theta, and we have to divide that through by m to find out just how much acceleration we'll get. So this is an example of where they did not ask about the tension, at least I don't think they did. I was reading carefully. They don't ask about the tension. So I'm going to take this formula, T sine theta equals ma, and write that down. And then I'm going to take the vertical component formula, T cosine theta equals mg, and write that down. And if I take equals and divide them by equals, that equation will still be true. And so I can cancel the t's on the left side, I can cancel the m's on the other side. Now that's interesting because it's saying whatever we end up with doesn't depend on the mass of the ball. So the ball could be 10 times heavier, and if it's, what is it going to depend on? If it's at the same angle and the same gravitational field, you're going to get the same velocity. So we'll talk more about that, I guess, when we get all the way through here, and we're just about there. So these are going to cancel, and that leaves us with an acceleration that is g, so it does depend on which planet you're on, because it depends on the gravitational field, and it depends on the angle. So depending on how we choose to set this up, we could have it spinning really fast. If it spins really fast, it's going to need more tension, and that means that the string will swing out more until it gets enough tension to maintain the circular motion at a higher speed. Let's see what else we get here. So I guess we got to this. The acceleration is given by g tan theta, and then the final step would be to use our kinematic formula. So there it is. A is equal to v squared over r. What we're going to do is say v squared is r times a, and that's what I said right here. And then the acceleration is g tan theta. And again, this is one of those where you step through it. This is my recommendation. Step through it one step at a time and tell yourself what you're doing at each step. Sometimes what happens is students say, oh, the answer on this was rg tan theta square root, so I'll just write that down. Here's my diagram, that's the answer. But they don't know they don't know the steps, they don't know the reasoning that goes between that. So if you're given a problem like this, you're going to be expected to be able to show your work and your reasoning. You're going to be able to want to go through and set up these formulas and carry them through and carry out the algebra until you've got a result for what you set out to come up with. And so taking this formula, it says that for this motion to be taking place, the speed at which this will be rotating is going to be given by rg tan theta square root. So it does depend on what planet you're on. If there's a larger gravitational field, you're going to need a bigger speed for a given angle. And it depends on the oh no. Okay, the r here, okay, we got to go back and decide what r is. This one's going to have to be rethought through, huh? Because r is equal to L sine theta. So I got to go back through and change this. Or you guys can. So I put in the r. I never made the substitution back. This is going to need to be L sine theta. And so this is going to be L. Now the sine theta, we're going to pick up an extra factor of sine theta, huh? Yep. Okay. So this is going to need to be L sine theta here. And that's going to change the angular dependence. We're going to have a tangent theta times a sine theta. It looks like we're going to have both of those in. And did we solve for the period? No. So again, read the problem carefully. And you guys can do the period from here. How would we do the period? So the period is going to depend on the distance. Now the distance that we travel all the way around is going to be 2 pi r. And so to calculate the period, we can take 2 pi r and divide through by the speed. So 2 pi r over the speed. And then again, we can take the r out and replace the r with L times the sine of theta. That's the value for r from the setup that we have. Okay, and that'll get everything back in. So I've got this in terms of r, but we really want to get it back in terms of L and theta. We want to see all the theta dependence clearly in the example. All right, let's move on. Here is a car driving along a highway, and this part of the highway is curved. So we're just going around a curve, no big deal. We go around curves when we're driving all the time. Now, the thing to realize here is when you're in a car and you set stuff on the dashboard, what's going to create a problem with things falling off the dashboard? And you go, well, the things that cause problems are accelerations. As long as I move at a nice steady speed, everything stays just sitting where I placed it. But if I accelerate forward, things fall off the dashboard backwards relative to the dashboard. If I slam on the brakes, objects slide forward relative to the car. If I turn left, objects appear to go off to the right. Now, what's really going on here? And what we can do is we can get somebody up here making an observation in their helicopter, looking down on this car, and we can see the passengers here. Now, as we're going around the curve, the tendency is for every object to go in a straight line. Now, the car would go in a straight line if there weren't forces. What forces are making sure that the car maintains a circular path rather than a straight line? So the forces acting on the car will be frictional forces. So we looked at that back in chapter 4. Frictional forces from the car, from the tires, where they're in contact with the pavement, are going to, here's the force on the car, the frictional force is on the tires pushing them this direction. Remember, if the roadway's frictionless, if there's ice there, you know, if the highway is frozen over with ice, we're probably not going to have enough frictional force to be able to steer that car. It'll tend to go in a straight line. But this car does have enough friction, and so it's going to be able to maintain circular path. Well, all the objects inside the car are still thinking, hey, I'm going in a straight line. And objects in the car will continue to go in a straight line until some force pulls them off into that circular path. So as far as this passenger, you know, now if the passenger is sitting in the car seat and they're paying attention and they see the curve, what they're going to know, what they've learned to do in a car when you go down a curve, is you lean a little bit, right? You lean a little bit, and then the force of gravity is tending to pull you to the side, and a little bit of that effect means that the normal force acting on you tips, and now you've got a force pushing you towards the acceleration. But if you're in a car driving and you're not paying attention, and suddenly the car goes through a sudden curve, an acceleration, the tendency here is the passenger goes straight and the car curves. Now what the passenger experiences, what it looks like from inside the car, is that, well, there's two ways of looking at this. I'm going to say the way to think about it is the car accelerates into the passenger, right? Passenger goes straight, car curves, side of the car curves, and the door on the side of the car runs into the passenger and brings them on board. It runs into the passenger, and at that point the passenger does accelerate towards the center. Okay. If the door's not closed, if the door flies open, there's always the possibility a passenger just goes straight, the car moves away from the passenger, and the passenger ends up out on the pavement. Right? So make sure the doors are closed securely and locked. I don't know if this has happened to you. It happened to my mom one time. The door was not completely closed. She wasn't paying attention, and went around a sharp curve, and the door swung open, and it was only the seatbelt that kept her in the car. And then once they straightened out again, she was able to reach out and pull the door back in, but the door just did not get closed and swung open. So be careful. Anyway, that's what's going on with this car going around the curve. So let's take a look and see. Here we go. Here's a picture of a speedway. Now you can see all these skid marks. You can see how many cars coming around this turn were successfully made it around the turn, versus the cars that skidded and they just slid, right? So once you've lost that static friction contact with the pavement, then you're going more or less in a straight line. This is nearly straight, right? You're just skidding off the road. So as long as the tires don't slip, the friction is static. But if the static friction gets broken, if we require forces above and beyond static, then we're left with kinetic. Now kinetic has, operating your car with kinetic friction is really dangerous, and here's why. First of all, the kinetic friction force is smaller than static, so you don't have as much friction force to work with. But probably even more important is that the static frictional force can be directed to the direction that you want. So static frictional forces can be directed so they're pointing forwards or backwards or left or right, depending on how you got the steering wheel turned. But kinetic frictional forces tend to oppose the direction of instantaneous motion. So if you go into a skid, the tendency is to keep going in the direction that you're traveling. Okay? It's harder to use kinetic friction to maintain the direction you want driving a car. So be careful, always use static friction. That's the solution here. So let's take a look and analyze, using a force diagram, an example. Now they call this skidding on a curve. I don't want to call it skidding. Well, we could. Anyway, let's take a look and see what happens here. Let's not assume we're skidding quite yet. But here's a car, it's coming right towards us, which seems kind of dangerous, but you have to, in order to do this force diagram, you have to stand out in the middle of the road. The car's coming around on a curve, so you're hoping it will curve out of the way before it reaches you. But this is the front view, and that's the top view, and I think they're both good to have. I think you want to draw both views when you're doing the force diagrams. This one is really nice for showing the normal force, the gravitational force, and the frictional force. Now that's static friction, we're assuming, unless we're skidding. Never mind, it could be either one. And so the frictional forces are really coming from the four tires in contact with the pavement. So that frictional force is some combination of those frictional forces at the location of the tires that we're working with. Now the top view is nice because you can see the circular motion. Now they haven't shown it here, but when I get to the diagrams that I've drawn, we'll be able to see the circular motion more easily using the top view. So front views, top views, a couple different views are really good for stopping and thinking about what's going on. In fact, practice drawing both of these. You could easily be asked to do something like that. Now the car is traveling, in this example, 15 meters per second. We're told that that's about 54 kilometers an hour. It's probably 30, 35 miles an hour. Will the car be able to stay in the curve, or is it going to skid? I see what's going on here. They're saying at this speed and at this radius of the curve on the road, it says the pavement is dry. The coefficient of static friction is 0.60. And then in part B, we're going to come back and say what happens if it's icy and the static coefficient of friction has dropped to 0.25. I think we can already kind of tell what's going to happen here. I'm guessing that with the dry pavement, maybe we have a good chance of making it around the curve. And then with the ice, things are going to be a little less certain. Okay, so here is my top view. There is the circle. That's the direction of velocity. That's the direction of acceleration. And we need a force. Oh no, I didn't draw the forces in. So gravity is into the board. That's mg. Normal force is coming out of the board. That's n. And then frictional force is towards the center. So get those forces drawn on that one. This one looks nice. So here we've got the normal force, here is mg, and here is static frictional force. Now, I avoid using a front view because I always feel like I'm going to get run over by the car. So I use a back view instead, and you can tell, see there's the license plate. I should have drawn in some taillights. Taillights, license plate. So I'm going to do a back view, works the same way. Velocity is into the page, right? And acceleration is towards the center, and the acceleration is working. We have an acceleration thanks to the frictional force. Without the frictional force, we would not be able to have an acceleration. We would not be able to maintain circular motion, and that's what we want. So what we're going to do is this. We are going to solve this so that we're right at the limit. If we use every last little bit of frictional force, static frictional force that we have, how, what would, I guess what we're solving for is what would the coefficient need to be? So what sort of coefficient would we need? That'll answer both questions. So let's do this. We're going to take the frictional force and say we're looking right at the limit, and that maximum value will come from using our static coefficient times the normal force. Now from this diagram, I can see that mg and the normal force I can set those equal because there's no acceleration vertically going on. So I'm going to say the static frictional force, the maximum static frictional force we could have, is given by mu sub s times m times g. So it's saying a heavier car, a car with more mass, is going to have a larger gravitational field, a larger gravitational force, It's going to have a larger normal force. The tires are going to be pushed more forcefully into the pavement. And that says that we've got the possibility of more friction. So if I have a car that's twice as heavy or 3 times as heavy, the gravitational force will go up by a factor of 2 or 3. The normal force will go up by a factor of 2 or 3. The maximum frictional force will go up by a factor of 2 or 3. So that's good to know. Not only do the gravitation and the normal forces go up, the frictional force will also get larger, or the limit of friction force will increase. So that says that the acceleration, which is entirely due to friction, I can calculate that as friction static over mass. When I substitute in the expression, the forces have gotten larger, but the inertia has gotten larger. And so if friction really behaves this way, if we really have friction that is proportional to the normal force, then the acceleration that we need will depend. The maximum acceleration we could possibly end up with would be mu sub s times g. So it just depends on which planet you're on, and it depends on what the static coefficient of friction is. Now, we can come back to our kinematic formula, and what we can ask then is, what is the acceleration taking place for this car? They told us that the car is traveling at 15 meters per second, and that there's, where was the radius? I guess I need to read more carefully. There it is, 50 meters. So a 50-meter radius, 15 meters per second for the velocity. So that says that the acceleration we are going to need is 4.50 meters per second squared. So let's see what happens here. The mu sub s that we have is going to be given by the maximum acceleration divided by g. So remember, this part was solved assuming that we're right at the limit. So it says that in order to make it around a curve on this roadway, we would need to have a coefficient of static friction at least as large as the acceleration that we intend to go through the curve with, divided by the gravitational field. So it does depend on what planet you're on. If you've got a larger gravitational field, you can go around curves faster. Good to know, right? So if you're driving around on Jupiter, you should be able to go around the curves faster with the... you won't need as much of a coefficient of static friction. But putting the numbers in now, we've got 4.50 divided by 9.8. It says that to make it around the curve at this speed in Earth's gravitational field, independent of the mass of the car. So that part doesn't matter, but the planet does. It says that we would need 0.46, doesn't depend on mass. Now, that, I think, answers our question, right? Let's go back and look. So 0.46 is what we need, and so that says the nice dry pavement, we're going to be okay, but we're not going to be able to make it through this curve at that speed. We're going to have to slow down if there's ice. So we are going to really need to slow down on that curve. We could go back and find out what speeds we could travel at for the two different conditions. Now notice, I actually put a value of mass in here just to give an example. Let's say that we have a 1,000-kilogram car. We didn't have to use it. So I didn't need to use the mass because the mass is canceled out. So sometimes that happens. We'll see examples where it doesn't. Here's another option for getting our car around the curve. Instead of depending entirely on friction, what if we put the curve up on an incline? So here's a front view again. Here's the car coming towards us. And what we call this is banking. Banking a curve means that instead of keeping the roadway level, we tip the angle of the roadway from side to side. And what that does is it takes a normal force that used to be vertical and it tips the normal force. So the normal force now is tipped at whatever the angle of banking is. So that's our banking angle. The normal force now has both a radial and a vertical component to it. The vertical component is going to be normal times the cosine of theta. The centripetal component, or radial component, is going to be the normal force times the sine of theta. Now mg is still downwards. Now in this example, we've got a banking thing going on. Should we change the coordinate system? Do we want to tip the coordinate system x, y? And we don't. And here's why. We want to keep the coordinate system where x is horizontal and y is vertical. And the reason why is that the acceleration is still horizontal. The acceleration is towards the center of the curve, and this roadway is banked. It's not changing elevation going up and down, it's maintaining this same elevation. It's just that it's going around in a circle and the roadway is tipped. So the center of circular motion is still over here somewhere. The center of circular motion is not down there. It's up here. The entire circle of circular motion is at this elevation that we're seeing right here. So it's going to be easier if we keep the acceleration just in one direction. We could break the acceleration up into components, but usually that's harder to think about. It makes the problem a little more difficult. So we'll stick with the acceleration, or we'll stick with the coordinate system rather, that lines up with the acceleration vector. More often than not, I'm going to say 95% of the time, that's the easier approach. And so x is going to stay here, and that means the normal force is what gets divided into components, not gravity. So gravity this time gets to just stay mg. It's entirely in the y direction, and that's it. So now they've come up with, here is the force. F normal sine theta is the force being used for this car to go around the curve. In fact, if you notice, they left friction out in this example. They are going to go around the curve. They're not going to use friction at all. So other than just enough friction to keep the car going in the direction the roadway is curving, but they're not actually using any force from static friction to help accelerate the car towards the center. They're going to do it all with this normal force. So they've taken that force, here is the normal force, here is the sine theta component, and set it equal to m times a. Now, that equation, it's okay, but it makes me a little nervous. As a physics teacher, what I find is, again, this is an example of, there's a lot of stuff going on in that formula, and I would encourage you guys, at least when you're starting out, I would say continue to do this, but at least starting out, separate out this formula into a force equation and a kinematics. Because what we have is we've got the kinematic stuff going on here. Acceleration is v squared over r. And then we have a force equation with a component of force and m times a. And if you put it all together, and that's in your notes, I'm going to say you might not be as clear on the individual steps. So typically keep more of those intermediate steps is my advice. So here's a problem where we're using a car traveling with some speed v through a curve. We're going to have a banking angle here, and it says what is the angle at which we could go around a curve with no friction at all? Which that's a challenge, right? It's the no friction challenge. So I'm going to take my zero friction tires and put on my car, and I'm going to make it around this curve. That's not a good idea. And make it around this curve just using the normal force. And so here we are. Here is the car. Again, this is my top view. Here is the velocity. Here's the acceleration. Gravity is going into the board, mg. Normal force is tipped now. So the normal force is not coming straight out, but it's rather tipped a little bit towards the center of the circle. So here is the back view. Again, here's the license plate. I left out the taillights again. I gotta get the taillights in there. So here is mg. Here is the normal force that's been tipped. When we turn that into a force diagram with separate components, I got mg downwards. I've got n that's tipped. That's going to be n cosine theta. That's going to be n sine theta, where theta is the angle of banking that we're working with. Now, looking at this diagram, I've got the vertical direction. There are no accelerations taking place there, so the vertical direction over here says n cosine theta equals mg. The radial equation says that the acceleration, which is circular motion acceleration, the acceleration that's taking place, maintaining the circular motion, is n sine theta divided by m. And I've used that trick that we've used before here. So I've said n cosine theta is mg, n sine theta is ma. I can set up my formulas like this. I can cancel out the normal force. I can cancel out the m's. And what I'm going to end up with then is tan theta is equal to A over G. Oh, look, the license plate's gone too. Tan theta is A over G, and A is equal to G times the tangent of theta. That's what we've ended up with. Now, if this is the back view, so there are the tires. See how the tires are straight on the side? That's clearly going away from us, I guess. So now what we can do then from this is we can make substitutions. We can use v squared is equal to r times a. That's our kinematic formula for circular motion. And so v squared will equal r times a, and a is g tan theta, so I can put that in. And then finally, they ask about the banking angles. So I'm going to solve for tan theta and say the angle at which we would want a roadway banked in order to make it around the roadway without using any friction would be given by tan theta v squared over rg. Now, putting all the numbers in, I converted this into meters per second. I got a very modest banking angle, 1.62 degrees. Let's see, I wasn't going super fast. This is only 13.9 meters per second. So that is, 30, 35 miles an hour. That's not, but it's a 50-meter radius on the turn. So it's not like I'm going around a sharp turn. I'm out in the countryside with a very gentle curve, and so I only need like a degree and a half to bank the roadway to make that happen. So, so check these problems. Go through them. Also double check. So I've checked them myself, but there could still be things going on, I realize. So anyway, check those problems and see. Now, what happens if the circular motion becomes non-uniform? And so that just means that at times I'm going faster. Let's see how that would get represented. I want to start with the acceleration here. So if I'm going around in a circle at a nice steady speed, I'm going to have a radial acceleration. But what happens if I'm going around a circle and I'm just going faster and faster and faster? So those circles are coming faster and faster. Well, in that case, if I'm going off in some direction and I'm picking up speed, there must be an acceleration taking place not just to the side, but in the forward direction. And in order to have an acceleration, I've got to have a force. So picking up speed along the circle means that there is an acceleration in this direction. We call that the tangential component. Now, it could be a tangential deceleration. It could be I'm going around in a circle and I'm slowing down, I'm not going as fast. So it could be that it's back in this direction. The velocity is here. The velocity is that direction, but the acceleration's here. That's slowing down. In any case, we've got two components. We've got a radial component and a tangential component, and they're at 90 degrees to each other if it's a circle. And so that means that we can combine them just using Pythagorean's theorem, and we can figure out what the total acceleration is, and that's kind of interesting to look at. But the bottom line is, in order to have a radial acceleration, I'm going to need some kind of a force in the radial direction. In order to have a tangential acceleration, I'm going to need some kind of a force in the tangential direction. Maybe it's the same force providing both, but often it's not. Often it is easier to think of this as happening in two independent directions rather than combining them into one vector. Now, if it's a car, if it's a car and I'm going around in the curve, I'm certainly using friction for both of these forces. The radial force would be coming from friction. The tangential force would also be coming from friction. What we can also do to generalize this, and we're not going to do a lot of this, this is more informative, so when you're thinking about these circular motion problems and the circular motion equations, what would happen if, for example, here's an object that comes along it follows this curvy path for a while, but then it changes and follows this curvy path instead. Now, if you're out driving, which I imagine you are, so if I'm out driving, is there a sudden change? Does there tend to be a sudden change from straight to curved, and then back to straight again? And what tends to happen is this. Rather than a sudden change to a fixed radius of curvature, usually there's a gentle increase in the radius of, let's say this, at first the curve is very gentle, and then it gets to be sharper. So it starts out with a very large radius of curvature, and then it gets shorter as you go around the more extreme part of the curve, and then it levels off. So it's not like straight line attached to a circle attached to a straight line. It's more like the radius of curvature is steadily changing. Well, that's why we said up front that the formulas that we've derived here are instantaneous formulas. So it could be that the R is changing. It could be that V is changing. Well, whatever R happens to be at some point, and whatever V happens to be, the acceleration can still be, the radial acceleration can still be calculated as V squared over R. The tangential acceleration we can relate to the change in the magnitude of the velocity. Okay, let's move into the last topic in the chapter. So we've spent a good amount of time looking at friction, and we spent a good amount of time looking at circular motion. And now what we want to do is spend the rest of today looking at drag forces, air resistance, fluid resistance. If you're running something through the air or you're running something through water, right? You're operating a boat, or maybe it's a submarine or submersible of some type. If you drop something through the air, there's going to be air resistance effect on that. If it drops into the water, there's going to be a water resistance, a fluid resistance force. How are we going to describe those forces? Now, this gets complicated. So just like friction was a pretty complicated problem to deal with, resistive forces are pretty complicated. What we're going to do is we're going to do kind of the same approach we took with friction. With friction, we just introduced a simple set of rules to estimate how friction might be behaving. So by no means were those frictional formulas that we came up with, were those like high precision formulas. We're just kind of estimating how much friction there will be in a given circumstance. And we can do the same thing with drag forces. So again, there are engineers and scientists spending their careers looking at friction. There are also engineers and scientists spending their careers looking at resistive forces in fluids. And lots of interesting detailed stuff. Kind of a general statement here. At small velocities, the force, often the resistive force, is proportional to velocity, but at higher speeds, it becomes more like the square of the velocity. So these forces are going to be what we call velocity dependent. If something gets dropped, so here is this object, and it's just going to get dropped. There's a gravitational force pulling downwards, and there is a resistive force in the opposite direction. Now it's kind of interesting to me that they've got this minus sign set up here. They've got this minus sign set up on the force. That's not necessarily what we've been doing. That's kind of counter the convention that's been going on. Why is that? And what they're doing is they're saying that this force is opposite to the direction of velocity. So they're actually keeping directional information included in here. We're going to have to be careful about that, because when we set up the formulas, we have to decide in a given situation, do I need the minus sign there, or do I not need the minus sign? That's a little confusing, I think. So in any sense, in any way, the drag force on a falling object. Okay, so I read that carefully. And so here is the V as a function of time. And what's going to happen is this, if I just drop something. So what will happen is initially the acceleration is going to be equal to the gravitational field. But as the object picks up more and more speed, the resistive force gets larger. Initially this force is not there. When we first let go of the object, it's purely mg. But then this starts to kick in, and as the v goes up, this force gets bigger. At some point, I'm going to reach a speed where the resistive force, due to the air, is just as big as gravity, and then I won't pick up speed anymore. That's terminal velocity. So what it says is, if you drop something, it doesn't just accelerate at g the whole time. Because of the air resistance forces, it tips over and approaches what we consider to be terminal velocity. Now, if you want to get rid of an air resistance effect, go to the moon, right? The moon has no atmosphere. So at the moon, if you drop something, the velocity just steadily increases as you go through the gravitational field. Okay. If you get high above the moon, then the gravitational field varies, and that becomes a problem for chapters 6 and chapter 8. Okay, so we'll look at those kind of varying gravitational fields when we get to those chapters. But for places reasonably close to the surface of the Earth, or the surface of the moon, surface of the Earth, sorry, we're going to have a terminal velocity. That graph kind of represents what happens to the speed. Now, what we can say then is that at terminal velocity, bv, ignore the minus sign, and ignore the vector sign right now. So we could ignore those two. B times v in this direction is offsetting, I'm going to take out the vector sign here too, m times g in the other direction. And what that leads to is the formula they have of the terminal velocity is mg divided by b. Now, mg is easy enough to think about. It depends on how much mass the object has. It's going to depend on the gravitational field. But b is a little more complicated. B is a resistive force constant, or it can be called a drag constant. And it depends on the cross-section of the object. If the object is spread out like a parachute, b is going to be a lot bigger number. If it's more compact, if the object is more compact, there's not going to be as much air resistance. If it's built aerodynamically so that it can pass through the air without disrupting the air so much, then the b value will be smaller. So that really depends on details of what's going on. So I want to, okay, here's the cliff, here's the object, it's got mass m. We're just going to drop it. So v is going to be in this direction, a is going to be in this direction, displacements are going to be, everything's in that direction. And I think I'm even going to call this the x direction, I think. So x, I'm going to say this is x equals 0, and then it picks up speed, I think. So here's the force diagram, mg, bv, and that says that, so I've dropped the minus signs and just said it's a magnitude of b times whatever v is equal to. Now, in my acceleration formula here, I'm going to say a is equal to mg minus bv. Now, the way we've set up the coordinate system, v is positive. So v is a positive number when we drop this, and that says that putting the minus sign in here is going to work. The acceleration will tend to be increased by mg, but it will decrease, it'll be held back by bv, and then we put the whole thing over m. So again, the signs can be a little tricky. I think we've got the signs figured out. Now, at terminal velocity, by definition, at terminal velocity, b times vt matches mg. So the terminal velocity is going to be given by mg over b, which is what they were writing on the previous slide. but I think it was confused with all the vector signs and the minus signs and such. Now, how could we come up with a formula for V as a function of T for this type of resistive force? Now remember, we're using B times V. We're claiming that the resistive force is directly proportional to the velocity, and that's not necessarily true. They said in reality it's typically more complicated than that, but let's use this simple approach. So with this simple type of resistive force, we can take out the A and replace it with dV dt, and then just leave everything here. What I've done here is take the mg minus bv, bring it to this side. So I brought all the v's to this side, and then I took the dt over to the other side, and then I integrated. So if we start at rest at time t equals 0, this is what the formula is going to look like. And so we can integrate this expression. Now when we integrate this expression, this is going to become a logarithm on this side. Take a look at that integral. I'm hoping you guys have seen integrals of that level of complexity. So that left side of that integration, the left integration gives us a logarithm. The right integration just gives us a factor of t. So that's just going to become t over m. Now, we'll see how this all gets compacted, but we can rewrite this as the velocity as a function of time is equal to the terminal velocity times this interesting expression here, 1 minus e to the minus t over tau. That expression shows up in physics and in engineering a lot. And so t, or tau, this is actually a Greek letter tau, is what we call a time constant. It scales how much time it's going to take until some process occurs, and we use them all the time in exponentials. So a typical exponential would be, an exponential with a minus sign, would be something dropping off. 1 minus this exponential instead is dropping off and asymptotically approaching a final value. Notice in this expression, when t is equal to 0, v is equal to 0. And when t goes to infinity, v is equal to vt. So again, we're going to see this formula show up from time to time, and so it's worth spending a little bit of time looking at it. Now here's the details. I'm going to say you guys don't need to worry about this. Okay, this is something that we're putting up here for kind of completeness and kind of interest. I know, there are always students coming up and saying, what are the real details behind this? And so I've gone in and shown more of the details. So I'm bringing back that integration we had before. I actually like doing substitution. So I'm going to say u is equal to what's in the bottom of this, in the denominator here on this side. And then du would be minus b dv. And dv then, that we have written, is minus 1 over b times du. So I've taken these statements right here, the u, and taken out this piece and substituted that with u. And then I've taken out the dv and replaced it with 1 over b, minus 1 over b du. I ended up with an integration that looks like this. There was a minus sign left, and I put that over on the right side. Now, integrating this out, I'm going to get 1 over b, logarithm of u, evaluated between 0 and v. On this side, I brought the b over to this side. I've got minus b over m times t, evaluated between 0 and t. On this side, I'm substituting back in for u. This becomes mg minus bv. And that, when I evaluate logarithms at both limits, that gives me the logarithm evaluated at b minus the logarithm evaluated at 0. And that's going to look like this, right? Logarithms minus another logarithm is a logarithm of the ratios. And so that's what my left side looks like. This is minus b over m times t. and then I exponentiate to remove the logarithm. An exponential shows up on this side. Mg minus bv then is mg times e to the minus b over m times t. We're going to get a common factor of mg, and then finally I'm going to solve for v. V was right here, and that's what I've been solving for. And that's it. That's my answer. So you can see adding a little bit of air resistance makes the problem 20 times harder, right, than before we had air resistance. So, you know, the good side here is we're getting formulas that show more detail of what's really happening. The downside is the math gets more complicated, and it gets more complicated pretty quickly. But what we can do now is identify mg over b. Well, that was our terminal velocity that we showed from the diagrams on the previous slide. And the time constant that we came up with looks to be m over b. So that's the form that we said we could write this in, where vt is the terminal velocity, and that depends on mb and the resistance constant, the resistive force constant, and the time constant depends on m over b. Now what that tells us is if the time constant is longer, it's going to take more time to reach terminal velocity. And so what that says to us then is, if I have an object that's heavier, you know, there's always this question of, well, does a heavier object fall faster or slower than a smaller object? A big block of iron compared with a smaller block of iron compared with a really big block of iron. And what this is telling us is mass does make a difference if there's air resistance. Mass is able to punch its way through air resistance better than something with lower mass, especially when we have the same B value. Now, B was a resistive force constant, and we said it depended on the shape of the object and how much it would spread out. So imagine this. Imagine a ping pong ball and then a golf ball. They're about the same size, but the masses are different. So for a ping pong ball and a golf ball, B, the resistive force constant, would probably be the same, right? It's got the same cross-section. They're both similarly aerodynamic. They're both spherical shapes. But if M is bigger, and we know this is going to be the case, the golf ball is going to have a much larger terminal velocity. You know, if somebody drops a ping pong ball on your head from 100 meters up, not a big deal. If somebody drops a golf ball on your head from 100 meters up, that's serious. And then in terms of tau, an object with more mass will take much longer. It's not going to reach terminal velocity near as quickly. So the ping pong ball reaches terminal velocity very quickly, and it's not a very large terminal velocity. But the golf ball with more mass reaches a much higher. It keeps picking up speed for a much longer period of time, and it reaches a much higher terminal velocity. Good to know, right? Now, this formula, it's worth taking a little bit, a closer look at the formula and what some of its properties are. As time goes by, we can measure these in time constants. So when one time constant has gone by, we can go through and show that we are at 63% of terminal velocity. When 2 time constants have gone by, we're at 84, 3 time constants at 95. And that's a feature anytime we see this, the stuff in the parentheses, the 1 minus e to the minus t over tau function showing up in any physics or engineering application. We can set up a table like this, define some time constants, and figure out how much time it takes as we approach terminal velocity. So I put some numbers in. Let's say we have a mass of 60 kilograms, sounds like a person skydiving, and that their terminal velocity is 40 meters per second, gravitational field is 9.80. So I looked some numbers up, and it said that a skydiver, if they're spread out, can minimize their terminal velocity to be about 40 meters per second. So that's about 100 miles an hour. So if your chute doesn't open, you still only hit the ground at 100 miles an hour, right? That's much less than would happen if there were no air resistance. If there were no air resistance and you dropped from those high levels, you would be going much, much faster. Now, let's see what happens here. So the B value that we end up with, mg over the terminal velocity. So if the terminal velocity is 40 meters per second, I put in the values for mg. It says the B value for a skydiver with their arms and legs kind of spread out. The B value is 14.7 newtons per meter per second, or about 15 newtons per meter per second. What would the tau value be? And the tau value from this is 4 seconds. So what it says is, for this skydiver, the terminal velocity is 40 meters per second. And after 4 seconds have gone by, how fast are we traveling? Well, we're traveling at about 63% of that. So 6 times 4 is like 24, 25 meters per second. And then after 4 additional seconds, we're going 30 meters per second, 35, 30, 35. And then after 4 additional seconds, now we're traveling at like 38 meters per second. So we're going from like 25 to 35 to 38. We're approaching terminal velocity, and the time constant for each of these is 4 seconds. Okay, so again, it's a function that shows up a lot. We will get more chances to work with that. All right, here is the summary, and there's not much of a summary here. All they have is the frictional stuff. So that takes us through chapter. I'm going to leave it on this page. This one's more fun. So that takes us all the way through chapter 5. You guys are, high level operating, highly skilled dynamics specialists now. You know how to set up those force diagrams. You know how to include gravitational forces, normal forces, frictional forces, tension. You know how to deal with angles of incline. You know how to break the forces up into components, keep track of the x and y motions independently. We've done a lot of stuff. So this is, it's a lot of stuff that we've done. Keep working at those examples and keep developing those skills. Whatever questions come up, stop by office hours and we'll get those looked at.